Welcome to the lecture series on nonlinear programming. In the last lecture we have seen about convex programming problems. I told you that if we have a minimizing type of objective function subject to all constraint less than equal to type less than equal to 0. So, this we call as a convex programming problem if the objective function f and all constraints are convex. Okay. We have also seen some examples of convex programming problem and unconstrained optimization problem. We have discussed how we can find out optimal solution of a unconstrained optimization problem, and constraint optimization with equality constraints using Lagrange function also we have seen in the last lecture. Now, in this lecture we will see KKT conditions, what KKT conditions are and why convex programming problems are important, that also we will see in this lecture. Now, if we have a equality type constraints, then we use Lagrange function Lagrange multiplier method to find out the optimal solution of that type of problems. But if we have a constraint optimization with inequality type constraints, then we use Karush-Kantakar conditions to find optimal solutions of such problems. So, consider this constraint optimization problem with inequality constraint minimizing function fx subject to gix less than equal to 0, where f and gi from Rn to R are defined and assume that they are continuously differentiable functions. Okay. Now, what is a necessary condition? So, what problem we are taking now? We are taking minimizing fx subject to gix less than equal to 0 I from 1 to m. Okay. So, what is necessary condition? Let x bar be a point of local minima for the problem MP, MP is this problem, at which the basic constraint qualification holds. Then there exist multipliers which we are calling as KKT multipliers lambda I bar I from 1 to m such that the following condition hold. So, what are the conditions? Now, first condition is same as the Lagrange condition for the Lagrange multiplier method, and all these conditions are also important, and we are calling these conditions as KKT conditions. First condition is gradient fx bar plus summation I from 1 to m lambda I gradient of gi at x bar must be 0. Okay, lambda bar. Okay. The second condition is lambda I bar gi of x bar must be 0 for all I. Gi x bar should be less than or equal to 0 for all I. This is the feasibility condition, and all multipliers which are lambda I bar must be non-negative for all I. So, these conditions basically are called Karush-Kantakar conditions or KKT conditions. Okay. Here this lambda I bar are called KKT multipliers. Okay. In Lagrange multiplier method we have an equality constraints, that is why we do not require that lambda I bar or Lagrange multiplier in those problems are non-negative. Here we have less than equal to type constraints. So, here this condition is required that all multipliers must be non-negative. Okay. So, this is a necessary condition that if a point is a point of local minimum, then this condition always satisfied. Now, we come to the sufficient condition, sufficient part. If lambda bar and x bar satisfy these 4 conditions, okay, and f and gi are differentiable convex function, that is it is a convex programming problem, because if the function f and all gi's are convex, then we call such problems as convex programming problem, and here we are assuming that function and all constraints are convex, then x bar is a global minimum point of the problem MP. So, if this condition holds, for the convex programming problem, then the point x bar and lambda bar which we obtained solving these conditions is always a global minimum point of the problem MP. So, the proof is very simple. For the sufficient condition, proof is very simple. Let us see. Now, function f is a differentiable convex function. What does it mean? This means fx is fx minus fx bar is greater than or equals to x minus x bar transpose gradient of fx bar, and this must hold for all x belongs to S, where S is all x belongs to Rn such that Gix less than or equals to 0 I from 1 to m. That is a set of, that is a feasible set. Okay, S is a feasible set, and if f is a convex function, then this means fx minus fx bar should be greater than or equals to this condition. This we have already discussed. Again, gi is also convex for all I. This means gi of x minus gi of x bar must be greater than or equals to x minus x bar transpose gradient of gi of x bar, and it must hold for all x belongs to S also. And these conditions hold, it is given to us in the statement. Okay. So, lambda I bar are non-negative, so we can multiply by lambda I bar over here. Okay. It will not change the inequality because they are non-negative, and sum from I from 1 to m. So, what we obtain? This implies summation of lambda I bar gi of x minus summation of I from 1 to m lambda I bar gi of x bar should be greater or equals to x minus x bar transpose summation I from 1 to m lambda I bar gradient of gi of x bar. Okay. Because lambda I are non-negative, you can multiply by lambda I and add all the constraints, all the m constraints. So, we obtain this condition. Now, you add 1 and 2, adding 1 and 2. So, what we obtain by adding 1 and 2? It is the left hand side will be fx minus fx bar plus summation I from 1 to m lambda I bar gi of x minus summation I from 1 to m lambda I bar gi of x bar and greater than equals to. Now, what will be right hand side? You see this term is common in both the inequation. So, x minus x bar transpose will come out, and inside the bracket we will be having this plus this, and this from the first equation is 0. So, this will be equal greater than equal to 0 using the first equation. Okay. Now, again lambda is gi x bar equal to 0 for all I. So, the sum will also be 0. So, we can easily see that this is equal to 0 because lambda I bar gi x bar equal to 0 for all I. Then this means sum over I from 1 to m will also be 0 because for each I it is 0. And now, gi x bar is less than equal to 0 and lambda I are greater than equal to 0. So, this implies because gi x bar is okay, it is feasible, okay, x. So, x is any point in S and S satisfying this inequality. So, gi of x is less than equal to 0 for all I and lambda I bar is greater than equal to 0 for all I. This implies lambda I bar into gi of x is less than equal to 0. Non-negative and non-positive, the product is always non-negative, non-positive. Okay. So, this implies sum is also less than equal to 0 because each term is less than equal to 0. So, sum is also less than equal to 0. So from here we can say that fx minus fx bar will be greater than or equals to negative of summation I from 1 to m lambda I bar gi of x, and this quantity is less than equal to 0. This means negative will be greater than equal to 0. So, this will be greater than equal to 0. So, what we obtain from here? We obtain that fx bar is less than equals to fx for every x in S, because S is an arbitrary point in S. That means for every feasible point x in S, fx bar is always less than equals to fx. That means x bar is the global minimum point. So, what we have proved, that if any function f and constraint gi satisfy these 4 conditions along with f and all gi's are convex, then the x bar which we obtained by solving these condition is always be a global minimum point of this problem, okay. So, these are sufficient condition. And let us discuss few examples based on this. So, this is the advantage of or application of convex programming problems, because convex programming problem makes KKT condition sufficient. It is only because of convex programming problems, that is function and all gi's are convex, the KKT conditions become sufficient, okay. So, let us discuss the first problem, minimizing f equal to 2x1 plus x2 subject to x1 square plus x2 square less than equals to 4 and x1 minus x2 less than equal to 0. So, how to solve this problem? So, this is g1, g1 is nothing but x1 square plus x2 square minus 4 less than equal to 0, and this is g2, g2 is nothing but x1 minus x2 less than equal to 0, okay. So, first we will see whether this problem is a convex programming problem or not, because then only the KKT conditions will be sufficient, okay. Now, it is a minimizing type problem and all constraints are less than equal to type. So, it will be a convex programming problem if the function and all constraints are convex. So, function is linear function, so it is obviously convex, okay. The first constraint g1 is Hessian matrix is 2 0 0 2. So, lambda 1 is 2 and lambda 2 is 2. You can easily see the eigenvalues of this matrix is 2 and 2, which are greater than 0, okay. Lambda 1 and lambda 2, lambda 1 is greater than 0 and lambda 2 is greater than 0, you can easily see. So, this is positive definite, that means function is strictly convex and hence convex, okay. And the second constraint is a linear constraint, so it is obviously convex. So, therefore, it is a convex programming problem. So, let us write down all the KKT conditions and try to find out the x bar satisfying the KKT condition, that will be a global minimum point of this problem by the sufficient KKT condition, we can easily say, okay. So, we will try to write down the KKT conditions. What are the KKT conditions? KKT condition is gradient fx bar plus, now here we are having 2 constraints. So, 2 KKT multipliers will be involved, it is lambda 1 gradient of g1 x bar plus lambda 2 gradient of g2 x bar equal to 0. So, what does it imply? It is, you can take x bar or x, it hardly matters, okay. You can take x also, that x that satisfy this condition will be the global minimum point. So, what is gradient of gx? It is 2 and 1, lambda 1. First with respect to x1, then respect to x2, lambda 1, gradient respect g1, g1 with respect to g1, del g1 by del x1 is 2x1, del g1 by del x2 is 2x2 plus lambda 2, it is 1 minus 1 equal to 0 0. So, what we obtain from here, it is 2 plus 2 x 1 lambda 1 plus lambda 2 equal to 0, and it is 1 plus 2 x 2 lambda 1 minus lambda 2 equal to 0. So, these are two conditions we obtain from here. Now, what are other conditions? Lambda 1 g 1 x equals to 0. So, this implies lambda 1 into x 1 square plus x 2 square minus 4 equal to 0, and lambda 2 g 2 x equal to 0. So, this implies lambda 2 into x 1 minus x 2 equal to 0. Again we have a feasibility condition. Feasibility condition is g 1 x less than or equal to 0 and g 2 x less than or equal to 0, and lambda 1 lambda 2 both must be non-negative. So, these are the KKT conditions. Now, how to solve these conditions, let us see. Now, from these two conditions we see that this into this is 0, which is possible only when either this is 0 or this is 0. Okay. This into this is 0, this means either this is 0 or this is 0. So, that means we will be having 4 different conditions, 4 different cases. So, we will take case 1. Okay. Let us take case 1. Case 1, when lambda 1 equal to lambda 2 equal to 0. Okay. Case 2, when lambda 1 equal to 0, lambda 1 means 0 means this condition hold, and suppose this is lambda 2 is not 0, this is 0. We can't talk about lambda 2, this is 0 suppose. Okay. Now, case 3, when x 1 square plus x 2 square is equals to 4 and lambda 2 equal to 0, and case 4, when x 1 square plus x 2 square equal to 4 and x 1 minus x 2 equal to 0. So, these are the only 4 cases which can be obtained from this condition, okay, from these two conditions. Now, suppose the first condition lambda 1 lambda 2 equal to 0. If lambda 1 lambda 2 equal to 0, then from these two conditions 2 equal to 0 or 1 equal to 0, which is not possible. So, this condition is not possible. Okay, this condition is not possible. Now, suppose lambda 1 equal to 0. If lambda 1 equal to 0, so from here lambda 2 is minus 2, and from here lambda 1 is lambda 2 is 1, which is again not possible because lambda 2 will be having only one value, and that must be non-negative also. So, this case is also omitted. This case is also not possible. Okay. Now, take out the third case, when lambda 2 equal to 0, lambda 2 is 0 and x 1 square plus 2 square equal to 4. Okay. So, when lambda 2 equal to 0 and this hold, then what we obtain from this condition? From this condition we obtain x 1 lambda 1 is equals to minus 1 and x 2 lambda 1 is equals to minus 1 by 2. Okay. Now, x 1 square plus x 2 square equal to 4 also. So, when you apply this condition x 1 square plus x 2 square equal to 4, what we obtain? We obtain minus 1 by lambda 1 whole square plus minus 1 by 2 lambda 1 whole square should be 4. So, what will be lambda 1 from here? It will be 4 lambda square will be the LCM, it is 4 plus 1 will be equal to 4, and that means lambda 1 will be nothing but from here what we obtain, it is 5 is equals to 16 lambda 1 square. So, this implies lambda 1 will be nothing but plus minus under root 5 by 4. Now, lambda 1 can't be negative. So, lambda 1 will be under root 5 by 4. Now, if lambda 1 is under root 5 by 4, so what will be x 1? X 1 will be nothing but minus 1 by lambda 1, that is minus 4 by under root 5, and x 2 will be nothing but minus 1 by 2 lambda 1, that is minus 2 upon x of under root 5. So, these are the x1 x2 we obtain from here. Now, we have to see that all the conditions are satisfied at this point or not. Now, this condition obviously hold because x1 square plus x2 square equal to 4, this condition is satisfying. So, this is this is holding. Now, x1 minus x2 less than equal to 4, what is x1 minus x2? It is minus 2 upon root 5, which is less than equal to 0. So, yes, this condition also hold. So, hence at this point all the KKT condition hold, and the problem is a convex programming problem also. So, any point satisfying the KKT conditions along with f and gi all convex, then that point is always a global minimum point of the problem. So, we can say that this point is a point of global minimum of this example 1. Now, similarly, let us try to solve the next problem. What will be f here? F is nothing but x1 square plus x2 square minus 2x1 and subject to, and it is minimizing, okay, minimizing f, and subject to x1 square plus x2 less minus 1 less than equal to 0. So, it is G1, the first constraint. Okay. So, first we will see whether the objective function all constraints are convex or not. So, what will be the gradient of Hessian matrix of f? It is 2 0 0 2. So, it is clearly convex because lambda 1 and lambda 2 both are 2, lambda 1 equal to lambda 2 equal to 2, and both are strictly greater than 0, means function is, means this matrix is positive definite, hence strictly convex, that means function is convex. Okay. And Hessian matrix of G1 will be, it is 2 0 0 0. So, lambda 1 equal to 2, which is greater than 0, and lambda 2 is equals to 0. So, this means Hessian matrix corresponding to this G1 is positive semi definite and hence convex, hence G1 is convex. Okay. So, this problem is a convex programming problem clearly, okay, because objective function f and the constraint G1, only one constraint is here and this constraint is also convex. So, this problem is a convex programming problem. Now, we will try to solve the KKT conditions, and the point which satisfy all the KKT condition will be the global minimum point of this problem. So, what are the KKT conditions? Let us see again, gradient of fx plus, here only one constant is here. So, lambda 1 gradient of g1 x equal to 0. This implies gradient of g is 2x1 minus 2, 2x2 plus lambda times gradient of g1 is 2x1 and 1, which should be 0 comma 0, and this implies 2x1 minus 2 plus lambda into 2x1 is 0, and the second implies 2x2 plus lambda equal to 0. Now, the other conditions are lambda 1 into g1x should be 0, this implies lambda 1 into x1 square plus x2 minus 1 equal to 0. Next condition is g1x must be less than equal to 0, this implies x1 square plus x2, this is a feasibility condition, this must hold, and lambda 1 must be non-negative. So, these are the 4 conditions, KKT conditions. Okay. Now, again from this condition we will having 2 cases. So, case 1 when lambda 1 equal to 0, and case 2 when x1 square plus x2 minus 1 equal to 0. Now, if lambda 1 equal to 0, if lambda 1 equal to 0, or this is lambda 1, okay, this is lambda 1. So, if lambda 1 equal to 0, this means x2 equal to 0, and when lambda 1 equal to 0 here, this means x1 equal to 1, and 1 comma 0, if you take 1 comma 0, 1 comma 0, 1 and 0 is less than equal to is 0, which is less than equal to 0, equality holds. So, this point 1 comma 0 satisfy all the constraints. So, this is the point of local minima. Oh, we are interested to find out only one solution satisfying all the constraints. So, this case is satisfying, this case is giving us one point which satisfy all the constraints. Okay. So, no need to solving other cases. Okay. So, 1 comma 0 is the point of global minima. So, that is how using KKT conditions we can easily find out the global minimum point of a problem. Now, without the convexity assumptions of F on F and GI, the KKT conditions are not sufficient for a point x bar to be local minimum or global minimum. These conditions are must. Convexity assumptions on F and GI for all I are the sufficient conditions. Okay. Without these conditions, we can't say that the point x bar is a local or global minimum. For example, we have this problem. Okay. This is minimum of f equal to minus x2, subject to what are the conditions? Conditions are x1 square plus x2 square less than or equals to 4 and minus x1 square plus x2 less than or equal to 0. So, the first constraint is g1, which is x1 square plus x2 square minus 4 less than or equal to 0, and the second constraint is g2, which is minus x1 square plus x2 less than or equal to 4. You can easily see when you find del square of g2 is minus 2 0 0 0. So, here lambda 1 is minus 2 for this matrix, eigenvalue is minus 2, which is less than 0, and for second matrix it is 0, second eigenvalue is 0. Or you can use the test of principal minors to find out to check the definiteness of this matrix. Now, first lambda is negative and second is 0, this means this matrix is negative semi definite, hence this is the G2 is a concave function. So, this problem is not a convex programming problem. Okay. Now, if we write the KKT conditions for this problem, you see what are KKT conditions? Gradient of f, that is 0 minus 1 plus lambda 1 times gradient of g1, it is 2x1 2x2 plus lambda 2 times gradient of g2 minus 2x1 and 1 must be 0 comma 0. So, this implies 2x1 lambda 1 minus 2x1 lambda 2 must be 0 and minus 1 plus 2x2 lambda 1 plus lambda 2 must be 0, and lambda 1 times the first constraint, lambda 2 times the second constraint must be 0, and feasibility condition x1 square plus x2 square should be less than or equals to 4 and minus x1 square plus x2 less than or equal to 0, and multipliers must be non-negative. So, these are the KKT conditions. Now, if you see the point 0 comma 0, that is x1 0 x2 0, x1 0 satisfies this condition, x2 0 that means lambda 2 equal to 1. Okay. Now, x1 0 x2 0 that means lambda 1 equal to 1, lambda 1 equal to 1, lambda 1 equal to 0, because when you put 0 0 then this is non-zero. So, this must be 0, 0 0 satisfying this condition, 0 0 less than or equal to 4, 0 0 less than or equal to 0, and 0 1 satisfying this constant also. So, 0 comma 0 satisfying all the KKT conditions, but still 0 comma 0 is not a point of local or global minimum. Why? This we can see graphically. You see what are the constraints? The first constraint is a region inside a circle. You have this circle, the x1 square plus x2 square equal to 4, this is x1, this is x2, and when you take 0 0 0 0 satisfying this constraint, so shade is toward inside the circle. Okay. Now, the second constraint is the parabola x1 square equal to x2, that is this constraint. And when you take a point, say it is 2 comma 0, say 2 comma 0 if you take, to minus 4 plus 0 is less than equal to 0, it holds, that means shade is outside the parabola. So, what is the common region? This is the common region. This is a feasible set, feasible region. Of course, it is not convex, set is not convex, that means one of the constraint is not convex constraint, okay, that is clear. Now, if you take this point 0 comma 0, it satisfies all the KKT conditions, but it is not a neither a local nor a global minimum point, because you can see that you have to minimize minus of x2 or maximize of x2, and x2 is maximum at this point or at this point. So, maximum is here or here. So, this point cannot be a global minimum point of this problem. So, why it is not a global minimum? Because convexity condition is not satisfying. Okay. So, what I want to say that if KKT conditions hold at a point, it does not mean that that point is a point of global minimum, because for that point to be a global minimum, beside KKT conditions, convexity of f and gi is required, is must. Okay. So, that is all for this lecture. Thank you.